Yo, WB, this is JB Free. We're getting back to basics with the freestyle energies. We're doing universal gravity. Here we go, let's groove. Oh yeah, can you dig it? Right off the top of my head, here's what I said. Universal gravity. It's not depravity. It is the most amazing thing that you will see. We are in a planet that is so swell. It's my favorite gravitational potential well. Sometimes, though, you want to get away. So here's what I'm about to say. If you want to know what gravity is far from Earth, this equation we're going to learn, it is worth so much. It's the new concepts we got to touch on to get where we want to go, which may be far from Earth, yo. It may be in a different galaxy. It may be in a different universal cavity. Who knows where? But we are going to figure it out. This is why I always tend to shout about this stuff, because it's so exciting. Universal gravity, it is so inviting because it gives us the opportunity to see the big picture. You better listen, Mrs. and Mr., because this is beyond anything that we've seen before. It's so cool, it's really easy. As before, we're gonna do this without too much stress because universal gravity is the best, yo. So we're back to basics here with the freestyle, and we're coming back for some more smiles. Hey there, it's JB. We're back for our adventures in universal gravitation. Now, what's great about this is we finally get to get off this rock that we're on, the Earth. Now, don't get me wrong, the Earth is about as awesome as a gravitational well as you could hope for, but we now, with Newton's very, very simple equation, get to figure out what's happening between the Earth and the Sun, between the Moon and the Earth, between our solar system and the entire galaxy, and we get to figure out how we can escape from the Earth, escape from the Sun, even escape from the galaxy. So all kinds of cool stuff that we're going to deal with, and it's really actually quite simple. And we're going to start with a really awesome demonstration, which was done by one of my students, David Kesh. And we are looking at it right now. Now you may say, that is a really boring demonstration. It looks like nothing's happening. Let me just explain what's going on. What's happening is truly amazing, but it's just happening very slow. What we have here is a big old rock, big massive rock. And then we got another big massive rock down here. And then we have a stick that is held by, and we're looking at this from above, it's held by two strings. Some fishing line that's really easy to twist. So it's a long string that goes up here and it's held from above. So this is actually free to turn clockwise or counterclockwise, whichever way it wants. There's a very heavy mass right there at the end of this stick and another heavy mass at the other end of the stick. And we are right now watching in very, very slow motion an amazing demonstration, but the demonstration takes about a minute to complete. So let's go ahead and watch this demo at about 8 times normal speed. Go for it here. Let's say 16 times normal speed. Let's see what happens. Huh, those two things attract. Let's watch that again. There's 8 times normal speed. Those rocks are attracting those masses at the end. That actually took about a minute and a half to happen, but we watched it in just a few seconds. And that is because all masses attract each other. All masses attract each other. It doesn't have to be an Earth-sized mass. Any mass will attract any other mass. And with this very sensitive experiment that was done, you can actually see that happening. So when Cavendish did this experiment and did it very carefully, he effectively weighed the Earth. This is how awesome and powerful these equations are. We can weigh the Earth. So let's go ahead and get started with all this fun stuff. Okay, let's start with this. The equations that are needed to do all the derivations in this chapter. There really are relatively few of them. So why don't we go ahead and check these out. The first equation that we need is one that we've been using for a long time. Fg equals mg. That still applies, just that when we're talking about g, little g, we don't always know that. We don't know the acceleration due to gravity at some point. And this will allow us to figure that out for any planet, or what we're doing this week. We also cannot forget about the net centripetal force being mv squared over r. And again, this is not a separate force. We always got to figure out what is providing that force, and then we set it equal to mv squared over r. But as you may be able to guess, what do you suppose will be supplying that force in this chapter of universal gravitation? We'll find out. And this is the one new equation that we have, so I'll use a different color for it. The one new equation is the force of gravity, and this is the universal force between any two masses, big M and little m, will be big G, a new constant, times big M times little m, over r squared, where r is the center-to-center distance between the two massive bodies, the distance between their centers of masses. Okay, well, those are really all the equations we're going to need to do all the derivations, so let's just get started. So let's take a look at Newton's law of universal gravitation. So this is the one new equation that we must start with, and that is that the force of gravity between any two masses, big M and little m, we like to call them big M and little m because very often one is big and one is small, is equal to big G times big M, little m, over r squared, the center distance between them squared. Big G is a really small number. We only call it big G because it's a capital G. It's 6.673 times 10 to the negative 11th with these units. And these units allow everything else to cancel except for newtons. Notice that meter squared will cancel the r squared, meter squared. Kilogram squared will cancel these two mass kilograms. And then you'll be left with newtons when you do this. R, again, is the center-to-center distance. When you're talking about spheres, it's really the center of mass to center of mass. The force between two objects is always directed along the line connecting the two objects, and it's always an attractive force. Right now, we don't know of if gravity has a repulsive counterpart like electricity and magnetism does, but it's quite possible that this stuff they're calling dark energy, which is causing the whole universe to accelerate outward, that may be some kind of counterpart to gravity. We don't know. A lot of cool stuff yet to be figured out about this. So cool. All right, next up, so that is the universal law of gravitation. Fg equals big G times m1, m2 over r squared, although I more often use big M and little m for those. There it is. Now, let's connect this to what we already know, free fall. So it turns out that if you have Newton's universal law of gravitation, which is indicated right here on my shirt, and you can measure the acceleration due to gravity, if you can just measure one more thing, which is the radius of the Earth, you can actually find the mass of the Earth. So when Cavendish did his experiment, just like the one that I showed at the beginning of the lecture here, when he did this experiment he found the big G constant by carefully measuring the force between two known masses. When he found that, he actually was able to figure out the mass of the Earth. It's often said that Cavendish weighed the Earth. Really, he massed the Earth. But let's show how we can find that. Again, all we need to do is to determine the acceleration due to gravity, which you can do by timing and dropping an object. Pretty easy. And the radius of the Earth, which actually turns out to be quite easy to find as well. Back in 260 BC, Eratosthenes figured out the radius of the Earth, and he was accurate within what we think is about 1% because he used the unit stadia. We're not sure if he was accurate, but for a guy in 260 BC, that's amazing. We're going to be doing that similar derivation on our lab, so you won't be left out of that fun. We're going to figure out the radius of the Earth. Just by figuring out the radius of the Earth, and by knowing g, little g, the acceleration due to gravity in Earth, you can find the mass of Earth, we do need to know what Cavendish gave us, this constant big G. So let's go ahead and figure out how to do that. Now, this is our universal gravitational law right here. The force of gravity is equal to Gm of the Earth times the mass of our object right there over r squared. Now, the center to center distance, we've got, here's our Earth. It's got radius of the Earth and the mass of the Earth. How come we don't need to count the radius of our mass right up here when we're calculating the force of gravity? You might think about that for a second. How come I don't have to add to this radius of the Earth the radius of this mass? Well, it's because it's negligible. It's so small. This is obviously not to scale. If it was, this would be, this mass would go so far up in the sky that it would be hitting satellites that are orbiting the Earth. So this mass radius, the radius of this little guy is negligible compared to the Earth's radius. The Earth is about 6 million meters in radius. This thing's in the order of 1 meter in radius, so we can just neglect that. So if we use this universal gravitation law right here, but we combine it with what we know the force of gravity is on the surface of the Earth right there, we can just set mg, the force of gravity on the surface of the Earth, to this equation, the universal force of gravity, which is always correct. Now, this is only correct if you know the acceleration of gravity, little g. We got to be careful because that changes as you get up to higher altitudes. In fact, at the top of Mount Everest, g is something like 9.7 something. So we can't use this generally, but we can still use it on the surface of the Earth. We set that equal to the force of gravity determined by the universal law of gravity, and then we can solve for the mass of the Earth. That's all you need to do, and because Cavendish found that g value, we know this. Turns out the mass of the object doesn't matter. Let's go ahead and cancel that thing out. It just doesn't even matter. Both sides, m cancels. We know the acceleration of gravity. We know big G thanks to Cavendish. We know radius of the Earth thanks to Eratosthenes and many other people who have measured it. It's very easy to measure. We can solve for the mass of the Earth. And when you do this, you should get something like this. The mass of the Earth is about 6 times 10 to the 24 kilograms. So we say just by finding this big G value, Cavendish allowed us to mass the Earth. Some people call it weighing the Earth, but it's really massing the Earth. So once you got G, you got the mass of the Earth. And in fact, we can use this relationship to find the acceleration of gravity on any planet if we know its mass and its radius. Also, if you know the acceleration due to gravity on the surface of the planet and you know its radius, you can find the mass of that planet. So this is a very useful relationship.